Hey guys, how's it going? This is Waynick again. Picking up today where we left off. We're going to start with chapter 5, which, for those of you that are following along in class, that is over internal combustion engines. So, nothing else, let's just go ahead and get into it. Now, I'll go ahead and tell you the first half of this chapter is basically explaining how engines work, the piston moves and the valves open and things like that. Some of you, gearheads out there, you might understand a lot of these things better than other people do. And if you do, be a good refresher. You can skip ahead, just whatever you see fit. It might be a little redundant, but to some of you that don't have much of an idea of an engine, I'm going to try to explain the best I can. Now, in addition to that, there's only so many things I can do with a whiteboard and a marker. Like I said, if you're in my class, we've already had the day. Some of you were there that day. There's a lot of sickness that day, where I brought my little Briggs & Stratton lawnmower engine in, and I pulled it apart in class and passed the pieces around. So that hopefully gave you a little better idea. But in addition to this lesson, I'm going to post a couple of videos. No, just one video. Yeah, just one video. It explains how an engine works. It has some really good, computer animation. Some of those things kind of help you visualize a little better than I can. So the first half, like I said, is more explaining how the engine works. And I'm sorry to say this, but I got to do a lot of reading during that part, kind of verbatim stuff. Dr. Johnston, when he wrote this textbook, he explains things pretty well, probably better than I can. You know how I am. I get kind of distracted by things. So he has a very good, clear, concise thing. I'll probably stop and annotate a little bit, but that's all right. But the second half is more the math part of it. So I'll kind of go along with these pictures the first half, then I'll erase it, and then we'll get into some of the math of it. So with that being said, let's go ahead and get into this. Internal combustion engines are used for almost every aspect of modern agriculture. Engines sizes range from small, such as a weed eater, which is very small, to large, such as that power four-wheel drive tractor. So large tractors, trucks, semis, they all have the same basic principles in an internal combustion engine, just some are a lot bigger than others. This textbook will not thoroughly discuss internal combustion engine design or include all possible formulas or calculations used in their design, but will focus on the basic principles and their operation and fundamental calculations. So there are entire degrees, master's degrees, talking about automotive engineering, probably PhDs out there somewhere. A lot deeper. This is extremely complex. You get into bore and stroke ratios and polished and ported heads. You get into all these things. So much deeper than we're going to go into, but it should give you a basic understanding of how it works. But just know we're not even getting on the tip of the iceberg. There's so much more to it than this. Before any calculations are introduced, it is critical to understand the basic principles of an internal combustion engine. Fundamentally, an internal combustion engine converts chemical energy in a fuel into mechanical energy that is generated and delivered at the crankshaft of an engine. So physics and chemistry, we're basically from that aspect, we're turning chemical energy into a spinning shaft, which you've heard me say 100 times in this class. If we have a spinning shaft, we can do a lot of things with it. We can turn wheels to move, we can turn a grinder, we can turn a hay conveyor, we can turn a bush hog, we can turn anything. So that's kind of the whole goal of an engine, is to take something chemical, relatively easy to carry around in a gallon jug, and turn that into a spinning shaft that we can take that gallon jug and turn it into 20 or 30 miles down the road, depending on how efficient your car is. The engine crankshaft may be connected to a number of devices in ways that utilize power. In a vehicle, for example, the crankshaft is connected to wheels through a transmission and drive shaft. In a tractor, the engine drives the wheels in a similar manner, but also turns the PTO shaft, which, like we said, most useful thing on a farm is the PTO shaft, which is used to provide torque to operate implements such as hay balers, crop harvesters, bush hogs, sprayers, everything under the sun. The steps taken to convert the chemical energy in a fuel to mechanical energy are the same regardless of type of fuel used. So, step one, air is introduced into the engine, oxygen more especially. Not as much the nitrogen and other thing, but oxygen, because we have to have oxygen to burn. 2, a quantity of fuel is introduced in the engine. 3, the air and fuel are mixed. 4, air and fuel are compressed. 5, air-fuel mixture is ignited. 6, combusting of the air-fuel mixture expands rapidly, causing a large pressure increase in the cylinder of an engine, which acts against and causes movement of the piston. So long, that was a long one. Step 6 means it all go bang. It makes big boom. Simple terms, it go boom. Through the connecting rod, number 7, through the connecting rod, the linear movement of the piston is converted into a rotary motion of the engine power shaft in a linear force of the piston that is converted into torque on the power shaft. So, and I'll get to these pictures in a minute, but the piston is forced down, which causes the crankshaft to rotate, is what step 7 is. Step 8, products of the combustion are exhausted from the engine. So then you blow all the smoke out of the engine and the process starts over. Shorthand version of this is step 1, air. Step 2, fuel. Step 3, mixture. Step 4, compression. Step 5, ignition. Step 6, expansion. Step 7, torque. And step 8, exhaust. So those are 8 steps we have to have. That was 5. 8 steps we have to have for an engine to run properly. There are 2 primary engine types used today. One is called a spark ignition or Otto cycle engine. These are your typical gasoline engines, 4-stroke and 2-stroke. And then what's called a compression ignition or a diesel cycle engine, invented by a man named Rudolf Diesel. In the spark ignition engine, a mixture of fuel and air is introduced into the cylinder, and after the cylinder is compressed, a spark ignites the mixture. That's why your car has spark plugs. It's to light the fuel and air, make it explode, make it go bang. In a compression ignition engine, air alone is introduced into the engine and compressed. Compression causes the temperature of the cylinder to rise as expressed in the ideal gas law. Some of you may know that. It is PV equals nRT, where P is pressure, V is volume, N is the number of moles of gas, R is the gas constant, and T is the temperature. So we're getting into some fun little physics there. But don't worry, I'm not a physics professor. I'm an ag professor, so we're not going to have to worry too much about that. You're welcome. At the proper moment, fuel is introduced to the mixture because the temperature is so high from the compressed air. The mixture combusts spontaneously, eliminating the need for a spark plug or a carburetor. So this is a diesel engine. These are your bigger trucks. They both have advantages and disadvantages. I tell you what, I'll post a second video. It's another video from Donut Media. I want to give a shout out to those guys again. They do some great videos, some really entertaining stuff over gas versus diesel engine. Like I said, I won't go too deep into it here because we're just going over the principles of an engine, which most of these principles go between diesel or gas. But it gives a really good rundown, super interesting video. It's another Science Garage video, like the horsepower versus torque video we watched last week. But yeah, I'll put that up. If I forget to, somebody message me, send me a text or something, remind me to put that up. There are also, so gas and diesel are 2 different, but there are also 2 different engine designs we use today, which are referred to by the number of times the piston has to travel the length of the cylinder to complete the 8 steps to create mechanical power. A 2-cycle engine, or a 2-stroke engine sometimes called, completes all 8 steps in just 1 upstroke and 1 downstroke of the piston within the cylinder. So this is what's called a 2-stroke engine. You don't see many of these in modern times. They were more common. Older dirt bikes, boat motors, they once again, they have advantages and drawbacks. What people have come to find a lot is that the drawbacks are a lot outweighing the advantages, and one of those big drawbacks that leads to regulation is they're not efficient. They put a lot of unburnt hydrocarbons into the air. They smoke. So if you ever go to say an indoor motocross race, I love motorcycles, you go to an indoor motocross race, even though when they're indoor they have to use what's called a smokeless oil in their mix. You have to put oil in the gasoline, so it's pre-mixed, but even though you use smokeless oil, it's still super smoky. Older boat motors are the same way. Pretty much the only place we see these now are in very small engines. So weed eaters, chainsaws, lawnmowers, those are the only things that are still predominantly two-stroke. And there are four-stroke versions of those as well. But two-strokes are really going away. Like I said, they have several drawbacks. And we'll talk a little bit about some of those in a minute. This action causes one full revolution of the crankshaft. So if we have this crankshaft here, and I'm going to get a little deeper into this, this piston goes down, the crankshaft turns 180 degrees, the piston comes back up, it turns the other 180 degrees, calling a 360 degree turn, one revolution. In a four-stroke engine, all engine steps occur in two upstrokes and two downstrokes in the piston of the piston in the cylinder. Four strokes occur over two full revolutions of the engine crankshaft. So a four-stroke engine makes two turns, and that's what we're going to talk about here. So I'll step off the book for just a minute, and we'll get into kind of how this works. So once again, excuse my crude drawings. Hopefully these will help a little bit, but we'll see. So up top, we have the typical four-stroke engine. Like I said, this is 99.9% of engines you're probably going to use in your life unless you own a lawn care business. Your car is a four-stroke. If you have a street-legal motorcycle, it's a four-stroke. Your tractors are four strokes. Your semis are four strokes. Your generator, if your power goes out, is a four-stroke. Pretty much every engine nowadays is a four-stroke. They're a lot more efficient. They burn cleaner. They're just a tougher engine, and like I said, so you'll see these a lot more than you'll see the two strokes. But we will talk about those a little bit. So first we have four strokes, and I'm going to name you off all four of those strokes. First is called the intake stroke. Now what I'm drawing here is you have a crankshaft turning. So you're looking at it from this angle, and it's spinning like this. And that's what this little egg shape on each of these is. You're not looking at it like this turning. You're looking at it from an end-on view. So stroke one, what is important here, it's called the intake stroke. And the reason it's called the intake stroke is because these are two valves. I've colored those in this kind of dark red color. And I'll zoom you up to it in a little bit. This dark red color, where when the intake valve is open, this orange denotes air or air fuel, whatever you want to call it, at what point, depending on what kind of induction you have. This intake valve is opened, the piston is going down, which creates a vacuum, and it sucks the air fuel mixture into the cylinder. When it gets to the bottom, the intake valve closes. Once it crosses bottom, that's when the piston starts going up. At this point, both valves are closed. This is stroke number two, also known as the compression stroke. Ta-da, the reason it's called a compression stroke is because it compresses the gases, which are fuel and air, in the cylinder. So stroke two is compression stroke. Stroke three is what's called the power stroke. Once this piston gets to the very top, and this crankshaft is at the highest point, holding the piston up the highest, that's an area called TDC, top dead center. That's the industry shorthand for it. Once it gets just to the top at the right moment, this little L I've drawn right here in all of them, that denotes the spark plug. It has a spark in the auto ignition cycle. So in the gas engines, you'll have this spark, and it'll go bang and light the fuel and make a big blast. In a diesel, it don't have the spark plug. It's just got such high compression that it just goes bang anyways, spontaneous combustion. Now, the reason it's called a power stroke is because this is the only one of the four strokes that actually causes movement. So it goes bang, it forces it down, there's an explosion, there's one way out, and it pushes that piston down, which creates the power. Once that piston gets to the bottom, if your car is tuned right, if your engine is jetted right, carburetor, fuel injection is all set up right, it will basically take the entire stroke to burn up all the fuel, and you won't have any unburnt fuel, and you won't have any time when the fuel is not burning. That's how you get the most efficient out of this. Next is what is called the exhaust stroke. So once it's at the very bottom of the cylinder, this exhaust valve opens and it pushes the piston goes up. Now this is for a couple of reasons. It could be because there are other cylinders helping turn it. If it's a one-cylinder engine, like on a one-cylinder thumper motorcycle, something like that. It could just be from centrifugal force and weights, counterweights, but the piston goes up nonetheless, and it forces the exhaust out the pipe, out the back of your car. Now, two-stroke is very similar, and I'm not going to go super deep into it, but the way a two-stroke works is it basically does all these things in two strokes, but the way it has to do this, the valves are basically on the side. They're what's called a reed valve. So instead of a mechanical valve with something pushing it open, it's kind of a backflow preventer. So you go blow air through, and when it builds compression, they slap together and it seals it off so that the air fuel mixture can only go one direction. One problem with this is you basically only have a half stroke intake, half stroke of compression, half power stroke before your exhaust starts going out the side exhaust port. And only half of a power stroke and exhaust stroke. So there's a lot of downsides to it. Once again, you have to mix the oil in most applications, so you're burning oil, which is not good for the environment. Also, the way it's made, you end up with your air fuel mixture off because you have some exhaust gases in the cylinder trying to burn instead of pure oxygen. And in much the same way, you have some air fuel, unburnt fuel going out the exhaust that is not that's not burnt, which is also bad for the environment. So there's a lot of drawbacks to them. You know, there are some more modern day applications. Detroit Diesel Engines, they actually made some huge two-stroke semi engines. Look them up on YouTube. Crazy sounding. They sound like a spawn of Satan, but they're really cool engines. Really cool engineering that goes into it. So I'll tell you what I'm gonna do. I'm gonna go ahead and stop this video, and then I will pick up on the next video. This one a little longer than I thought. We'll pick up on the next video with all the math. So I'll see you later.